Hello to everyone. So we are back with the Spotlight Seminar on AI initiative by the Italian Association for Artificial Intelligence. And as the president of this association, I'm very proud to start with the Spring Seminar Series of 2023 with a seminar held by Yoshua Bengio. I thank very much, Yoshua, for having accepted our invitation. And all of us really know him. He does not deserve any presentation, but still, I need to say a few words about Yoshua. He is recognized worldwide as one of the leading experts in artificial intelligence. He is very well known for his conceptual and intervening breakthroughs in artificial neural networks and deep learning. A few words about and he is a full professor in the Department of Computer Science and Operational Research at University of Montreal, and he is founder and scientific director of MILAB, the Quebec Artificial Intelligence Institute, which is one of the largest academic institutes in deep learning. I would like to mention that in 2022, he became the most cited computer scientist in the world, according to the H-Index. And he was made an officer of the Order of Canada and a fellow of the Royal Society of Canada. He became in 2020 the fellow of the Royal Society of London, and he received many prizes and recognition. I would just to mention that he is a Turing Award laureate of the Turing Award in 2018, which is basically the Nobel Prize of Computing, alongside with Geoffrey Hinton and Yann LeCun for their important contribution and advances in deep learning. In 2022, he was appointed Knight of the Legion of Honor by France and named co-laureate on Spain's Princess of Asturias Award for technical and scientific research. So we have really the pleasure to have with us one of the most influential computer scientists currently in the world, and really one of the father of the new deep learning era. So Yoshua, I'm very proud that you have accepted the invitation. That's really a great honor for us. And you will discuss a topic which is nowadays very hot and very important for our community. So how to envisage the creation of large neural networks that can reason. So I would also to take the opportunity to thank the board of directors now represented by Marco Maratea, Chiara Ghedini, and Giuseppe De Giacomo, which helps me in organizing all these seminars. So thank you, Yoshua, and please.
Thank you, Gianluigi, for the kind words, and thanks for the Italian Association for AI to have invited me. It's a pleasure to talk to you. Italy has a special place in my heart, has had for a long time. So let me see, move to my presentation screen. Right. I've been thinking for about 6-7 years about the question of what's missing in current deep learning if we compare the state of the art in deep learning and AI mostly with human cognition, human intelligence. And I think what we are seeing now with ChatGPT makes it even more urgent to figure out this gap and how we can potentially design AI systems that have both the advantages of what we already have with deep learning, but also fills this gap to have intelligence that's more powerful, as I will explain, and more like human intelligence. So what is missing from ChatGPT? And maybe different people have different opinions, but I'll focus on these points here that are interrelated. I will argue. But in a single word, I would say reasoning, and not any kind of reasoning, because in AI there's a long history of reasoning systems, but human-like reasoning, and I'll try to explain what I mean through the presentation. And that includes causal reasoning, the ability both to discover causal structure and to exploit it in order to take decisions. Something that's very concrete and practical and that people complain about with ChatGPT and other large language models is that they will just state things often with high confidence without sometimes, and sometimes making like very big blunders. So that's probably the reasoning part. So they can be confidently wrong, and then they cannot really do a good job of explaining their reasoning or the sources of information, the facts that they might be supporting their conclusions. Now, humans are not perfect at doing that, but we have developed that ability to some level that I think we should consider as an objective for AI systems. The other aspect of I mean, the first 3 points are kind of related to each other, but the last 2 points are also related to each other and are different from a different perspective, which is something fundamental in machine learning that has to do with generalization. Humans are able to generalize much better out of distribution, so in contexts that are quite different from the training context, and they can learn from much less data. So ChatGPT and GPT-4 are trained on huge quantities of data, from 1,000 to maybe 10,000 or more, the amount of data that a human could read in their single life, right? So there's something missing if we're not able to reproduce the kind of sample efficiency that humans seem to display. And it's good to start thinking about this. So let me focus a bit more on human-like reasoning. So when I use the word reasoning in this context, I really mean inference, and in fact, I mean probabilistic inference. And there's actually a lot of evidence from psychophysics, neuroscience, that humans reason in a Bayesian way, in a probabilistic way, even though we're not conscious most of the time that there are these other alternatives, except later maybe we think about another alternative, and sometimes it could be pretty close. So for example, the Necker cube image that you see here, this wireframe, you could like interpret it in your mind with either the face that is on the left as being in the front or in the back, and it's either one or the other, and your brain will kind of switch from one to the other. So it's like your brain is able to conceive multiple interpretations, and that there is uncertainty. And in fact, you can make experiments where, if it's not 50-50 like here, you might be able to ask people to make bets about what is the correct answer, and the probabilities that are implicit in these bets correspond to the correct Bayesian probabilities often. The other characteristic of human inference, besides this sort of probabilistic aspect, is that it's all about composing pieces of knowledge. Something that may happen to some extent in attention-based models like transformers, but in transformers, you have sort of a soft combination of pieces of knowledge or pieces of information from the input. Whereas in human-like reasoning, we actually have these pieces coming to our mind. These are the contents of thoughts. And those pieces are then combined sequentially to explain, plan, imagine, learn, and so on. And that requires a form of knowledge representation, which is quite different from what we have in deep learning. Although sometimes we do see specialization in the neurons in the deep net, it doesn't have this crisp kind of separation that we can observe in our own thoughts. So in my own work in the last 6-7 years, I've been highly inspired by neuroscience and psychology theories of how we think, and in particular, and of conscious processing in our minds. So in particular, one of the, if not the dominant theory about this is called the global workspace theory. And it sees what is going on in your mind as happening because of a bottleneck. You have lots of things going on in your brain, but only a few symbols corresponding to a thought are selected or emerging. So it's like if there is a compression or a selection, which is a form of attention, but it's a choice that is made that is stochastic. So that's connected to the probabilistic inference I was talking about. So the hypothesis that my group has been working on is that all of these missing ingredients in the current large neural nets, like large language models, are related to something that we are missing in current systems, and that essentially corresponds to the conscious processing that we have in humans, that we need to be able to incorporate that in our models. It's interesting to see when humans become acutely conscious of aspects of the world and interpretations and plans, and precisely it's when you're faced with novel situations. Like the example I give in many talks is, you've been driving all your life, let's say in continental Europe or in North America, where we drive on the right, and then you go and rent a car in Australia or in London, and there's this only one little rule that has changed, but it has drastic consequences for how we should behave when driving, of course. And humans are very good at adapting to these changes in distribution, whereas I think if we try this with our current approaches, it might take a lot more data. But what's interesting is the fact that your brain moves into a different way of processing information. So if you're in your usual town driving, you don't need to think about it. It goes in automatic mode, what's called habitual, and you can listen to the radio, you can talk to the other person in the car, your attention can be somewhere else, although that can be dangerous, but if something unexpected happens, actually. So when something unexpected happens, suddenly you have to pay attention. And that goes through this bottleneck that I was talking about. So this is connected also to the discussion coming back from the 60s and 70s and the work of people like Dan Kahneman, who got a Nobel Prize for his work, where we realized that in the way that our brain operates, there are these two modes of operation. I mean, he used the term system, but I think modes of operation, because they actually coexist all the time, or at least the system one part is always present. That's the unconscious part of what's going on in your brain. And then there is the part that emerges through this bottleneck, which is the system two part. So the system one part is essentially what we're doing quite well right now with deep learning. And it's able to learn and represent knowledge, but in an implicit form that is not always easy to verbalize. Like you can't really explain in sufficient detail to someone how to ride a bike, but you know how to do it. And faced with a new situation, you can have the right behavior. On the other hand, there are all of these things we can verbalize. So that's the system two part, usually through a sequential process, going through this bottleneck of symbols coming through your mind. And that's something very powerful. Of course, it's central to our use of language, but not just language. Reasoning, math, algorithms, planning in general, that is something you can be conscious of. And we can then explain to someone else what's going on through our mind, which would be very abstract and high level variables that you can combine in a kind of very powerful combinatorial way that gives you the ability to generalize to new configurations, like, oh, there's this one rule that changed. Okay, so there's this aspect that I've been really considering a lot in my previous work in the last few years about how could we design, say, neural nets that have some of these properties in particular, where knowledge is broken down into pieces that can be recomposed. And we can use attention mechanisms for doing some of that. But I'll argue that it's not sufficient. We're missing some of the expressive power of discrete stochastic decisions that current soft attention doesn't provide. So in humans, we are able to combine these pieces of knowledge on the fly with the system two kind of processing. And somehow we also learning these pieces of knowledge in a way that makes it easy for us to generalize to new cases where most of the pieces don't need to change, but maybe we need to adapt one of them. It's also reminiscent of how we design code, right? We try to break down our code into independent pieces. Independent here is not in a statistical sense, it's more like in an information theory sense, meaning that if you need to change one of the pieces, if your code is well designed, you don't need to change all the others, right? So that can be expressed formally, and it is related to inductive biases, if you want, like assumptions or preferences that come up in the discussions about causality. And this is an idea that really came from the work of Bernard Shopkoff as far back as 2012, this notion of independent causal mechanisms. So these are some of the inductive biases. And the inductive bias of causality is something I'm going to kind of spend more about, because it really may help us with this notion of out-of-distribution generalization that our current systems could be, better on. So this really is related to the basic assumption we've had in machine learning, that the examples are IID. And actually, unfortunately, the world is more complicated. Like, things change in the world, and somehow humans do a very good job of adapting, as I was saying earlier. So what kind of clues can we get from human intelligence, and how do they manage to reuse knowledge in such an efficient way, right? So if you take the causal perspective, which is very similar to, if you want, the physics perspective, you can imagine how knowledge could be represented in a way that really makes it easy to generalize completely out of distribution. So the figure on the top right here is an illustration of this. So if you've seen pictures of natural scenes all your life on Earth, and then you get to be on the moon or just see pictures from the moon, the actual distribution of these images would look very, very different. Like, they don't even overlap, almost very little. Like, very few images on Earth would look like images on the moon. Yet we don't have any trouble to make sense of that. Right? So, like, the distribution has completely changed. But what remains the same, right, is what allows us to generalize across distribution. So what remains the same, if you think about physics, is that the laws of physics are the same, right? So if you think of the laws of physics, you think of like maybe a stochastic dynamical system more generally, like differential equations with noise. And when you run those equations forward, you get some data that has some distribution, but it depends on initial conditions or the setting of some of the variables. So, for example, in the case of the moon and Earth, maybe the constant of gravity is the key thing here. That means that we have an atmosphere, we have life, and so on. The moon, well, it doesn't have a sufficient constant of gravity, so there's no atmosphere, and so on. So sometimes, a single change could lead to very, very different distribution. But if most of the knowledge is encapsulated in the causal mechanisms, then we might still be able to make sense of what we're seeing, even though it looks very different from what we are used to. So that's a motivation. And now, if we go a little bit more formal about the notion of causal model, so how is a causal model different from like a regular probabilistic model of the data? Well, I will argue that we have some inductive biases in the structure of a causal model, and one way that is special, that is really something related to causality. And one way to think about this is we have the observed variables, that's called V, but we also have these other variables, which in this slide was like the initial conditions or setting of some of the variables, which in causality we called interventions. So maybe somebody sets some variable and fixes it, or for different reasons it's been modified, and then when you set those variables, it really can have a cause and effect, trickle effect on the variables that you observe. So now really we have this joint distribution over the regular variables and like this like action variables, the intervention variables. And one way to think about this is that we if you consider just the observed variable, the observed or latent variables V, the regular variables, depending on the value of the intervention, like which are the setting of these intervention variables, you get a different distribution, right? So what you have is a family of distributions indexed by the interventions. So instead of having one distribution, you got this exponential number of distributions because the number of interventions, there are many intervention variables, and so you've got an exponential number of distributions in this family. But instead of these distributions being independent of each other, like you would normally think in probabilistic modeling, they all share the same parameters. It's the causal mechanisms. Once you know those parameters, you know the causal structure, and somebody tells me, here's the intervention that determines what the distribution will be. But because they share the same parameters, you can generalize across the members of that family. You might be able to see only some finite subset of interventions, and then figure out what is the causal model. But now you can generalize to new distributions corresponding to interventions you've never seen. So there's a form of generalization going on here across distributions because it corresponds to different interventions. Sorry, yeah. So that's really the key machine learning interpretation of why a causal model can be so much more powerful than a regular probabilistic model of the data. Okay. Now, in more details, when you choose an intervention, you might set some variables, which kind of changes the relationship between variables because you kind of block the effect of how if we set this variable, it means it doesn't respond to the values of other variables, but it might still have an effect on other ones. So we call this intervention surgery in the causality community. Also, the intervention may be observed or not, or partially. Maybe we know that somebody did something, but there were other things that happened that were other interventions, or we may not observe any of the interventions, but we can guess them. I mean, in fact, humans spend a lot of time guessing, like, who did what? That explains the weird thing that we're seeing, right? So our brain constantly tries to do inference over the interventions, because usually the interventions come from like agents, like other human being or an animal or something. Also, things could be complicated because the variables are not all observed. Like that's this typical case in probabilistic modeling. So because we don't necessarily observe the intervention, because we don't necessarily observe the variables, we need powerful probabilistic inference. We need to be able to figure out good guesses of these things we don't directly observe. But the important message from machine learning, the same thing I said in the previous slide, is that really when you start incorporating these ideas about causality, you're kind of constraining how you can model anything you observe. And that's good. I mean, especially if the world is causal, so you have things like temporal order, like cause must precede effect. You have more subtle things like what's called the marginal independence of causes, meaning that in general, if you don't observe the effect, then the causes are independent of each other. Okay, and also often we assume that the dependencies are sparse between the variables in a causal graph. So this sparsity is something that I work quite a bit on and is directly inspired by this global workspace theory that I mentioned and the bottleneck. So if you can only do inference by looking at very few variables at a time, then it's reasonable to assume that the only kinds of dependencies that you can represent are sparse, that involve very few variables at a time. So we can see that in language, right? So if you think about a sentence like, if I drop the ball, it will fall on the ground. This is actually quite interesting from a machine learning perspective, because we're making a prediction about one variable, like the position of the ball at the next time, and given very few other variables, like the fact that I had it in my hand and I dropped it. So in general, if you have many variables, this is just 2 or 3 or 4 variables out of millions of possible variables we could conceive, and in general, if you have a lot of variables, then if you want to make a good prediction about one of the variables, you need to know a lot of other variables. So think about predicting a pixel of an image. If you only use a few other pixels, even if you're allowed to choose which ones, you might not be able to make a very accurate prediction. So it's not true for the pixel level that you have that sparsity of dependencies, but it's true of the high-level causal variables that we can verbalize in language. So this is another inductive bias that we can exploit. Okay, so I've talked a lot about causality, and now I'm going to talk about, which is all already like complicated. I mean, it's difficult. There are a lot of open problems in machine learning, how to incorporate causality. Now I'm going to make it even more complicated because I'm going to say that we need to be Bayesian. And then later I'll tell you how we can do all of these things. Well, at least the path forward. Okay, so why should we be Bayesian? Well, because there is a lot of sources of uncertainty, not just because the particular example you're seeing has some ambiguity, but there's ambiguity because you have finite amount of data. That's the central thing about Bayesian machine learning, is that it says, given a finite amount of data, there may be many possible theories about multiple models. And in the case, if you want to be causal, multiple causal models, like multiple causal graphs. The causal graph is specifying which variable is direct cause of which other variables. So that forms a graph with the nodes being the variables. So there may be not enough data to know what is the correct causal graph. In fact, there are some theoretical results showing that in general, even if you have infinite amount of data, but it's only one intervention, so in other words, like no intervention, or it's a single kind of setting of the intervention variable. In general, if you're in this purely observational setting, as people call it, you will not be able to figure out what is the causal graph. That there's an infinite, or not infinite, but a combinatorially large set of graphs that may be compatible with the data, even if the data set is infinite. So this is called the Markov equivalence class. So there's this class of models or graphs that are compatible with even an infinite amount of data. So that's one source of ambiguity, because you don't observe enough interventions, basically. You can't intervene on everything in the world. There are things you can't directly access, like, we can't do experiments on the sun, for example. So there might be ambiguity about the theories that we have about the sun, because we can't like check our theories by trying out things on the sun. And then, of course, we don't have infinite data. We only have finite data, and that's usually what Bayesian machine learning is about. How do we represent that uncertainty coming from the finiteness of the data set? But if you learn a Bayesian posterior, let's say over causal graphs, given data sets D, that includes all of those sources of ambiguity due to the fact that you didn't observe enough interventions, and due to the fact that you have a finite amount of data, period. So why wouldn't we just be Bayesian and calculate the distribution over all the possible explanations, all the possible graphs, and so on? Well, in general, Bayesian inference is intractable. It requires an amount of computation that exponential in all kinds of numbers, like the number of variables that you're dealing with, and so on. For example, the size of a causal graph is super exponential in the number of variables. It's like 2 to the n squared or something like this. And so we somehow need powerful inference that can tackle that apparently intractable task. So it's intractable, but maybe we can make good approximations. So what we need is inference machines that can produce or represent distributions even when these distributions have an exponential number of modes. How is that even possible? Because we can't possibly list all those modes, but I'll tell you how this is possible in a few minutes. Now, I talked about the uncertainty about the causal graph, but you may have other sources of uncertainty that your Bayesian posterior can represent. So, for example, the parameters of your conditional distributions in the causal model, or your the fact that not all of the variables are observed. So if you only observe x's, there may be some z's that you don't observe. So you can use the same inference machinery to do inference over the things that vary from example to example. So the parts of the explanation for that particular example that we don't observe. So these are the latent variables. But we can also use use the same kind of machinery to do inference over the things that are the same across all examples, and that's things like parameters or causal structure and so on. And what's interesting is that the Bayesian posterior, so that's the equation at the bottom, even though it's intractable, it's proportional to something we can compute. So the thing on the right-hand side of the equation are things we can compute. So if you give me a graph and parameters and assignments of the latent variables, and I'm given the observations, I can compute the probability a priori of this graph according to my prior, the probability of those parameters according to my prior given the graph, and the probability for each example of the latents given the parameters in the graph and the data that we observe given the latents and so on. So all of that is computable. There's a little bit of an expensive thing because there's a product over all the examples, which is not exponentially expensive, but it's linear in the size of the data set. But as I'll tell you, there's again simple ways to go and make the actual algorithms able to make parameter updates without having to see the whole data set at once, but only little mini batches as we do in deep learning. Okay, so that's the Bayesian part. Yeah, maybe let me give you some more motivation for being Bayesian. So what being Bayesian, if you're able to do it, enables is to avoid being confidently wrong. So think of ChatGPT stating things as if they were true without saying, oh, maybe, no. It's saying that somebody went to jail or whatever, was accused of rape or something. There was something like this that came out, and it's wrong, right? So it states things with confidence that are wrong. And if you were Bayesian, it could not happen, because obviously in the data that was used to train this system, there is not enough evidence to be sure that this person was convicted of rape. And so the correct Bayesian posterior should have some uncertainty. Well, maybe they were, maybe they weren't, maybe there is no evidence one way or the other, so a priori probably not, right? And so you would have systems that are much more conservative, that don't state things that are false with confidence. And this is important, right? This is one of the big limitations right now of ChatGPT. So what I'm saying is, if you want systems that are reliable, then the right thing to do is to be Bayesian. Now, as I said, like people who have studied probabilistic machine learning and some know that there's nothing like really new that I'm saying. But why is it that nobody, I mean, like the state of the art is not using these things? It's because it looks intractable. Because you have a normalizing constant here that over all these things, and that normalizing constant is way too expensive, and we don't know how to sample from that distribution efficiently, at least. Okay, so now I'm getting to the part of my talk where I want to talk about how in the last couple of years in my group, we've started to tackle that by introducing a new framework for probabilistic machine learning, in which we train neural nets to sample from these posterior distributions. And in general, the approach is actually more general than that. What it does is it learns a sequential policy. So that's like the sequence of thoughts in your mind that constructs objects. So the object might be a theory, might be an explanation, a setting of variables, such that when the neural net is trained to minimize its objective, it will sample those objects with probability proportional to some given reward function. Okay, so I use the term reward function because this work emerged from thinking about this problem from a reinforcement learning perspective. But instead of the usual approach in reinforcement learning, which is look for a policy, a sequence of actions, I mean, a distribution over a sequence of actions that maximizes some reward function. Here, we're not trying to maximize, we're trying to sample with probability proportional to the reward function. So it's a subtle difference, but it makes a huge difference. So if we consider the thing on the right-hand side as a reward for having chosen this particular causal graph, particular set of parameters, particular latents. If we were to just to maximize the reward, we would find one setting of these things, one graph, one setting of the parameters, one setting of the explanations. And that's what we normally do in machine learning. We're trying to optimize to maximize the likelihood, which is the fit to the data. Whereas these GFlow nets, generative flow networks, as we call them, they're trained to sample in proportion to the reward, which means instead of finding one solution which fits the data, it's trying to find all the good solutions that fit the data. And that is exactly what the Bayesian posterior is. Right? So this is an important shift. Instead of finding one theory that fits the data, somehow find a way to represent all the theories that are probable that have a high reward, which means more precisely sample those theories with probability proportional to how well they fit the data, which is the reward on the right-hand side. Okay, so so this method is related to reinforcement learning, as I said. It's also related to variational inference, or more precisely, amortized variational inference. But it uses a different objective function. And I think I have a slide. Yes, I have a slide where I'll talk more about that. Okay, now it's also connected to classical method and sort of probabilistic methods to deal with this problem. So in other words, going back to this equation, there is a classical way to find the Bayesian posterior, which is using Monte Carlo Markov chains. And I don't have time to give you like a lecture on this, but these methods, if you sample long enough, will give you the right samples from the right distribution. So given an energy function, which is like minus log of this reward, you can apply the Monte Carlo machine, the Monte Carlo Markov chain recipes, and there are many variants, such that asymptotically through repeated sampling steps, you would converge to the right distribution. The only problem is that this asymptotically in practice may lead to exponential amount of computation to get really good solutions. So there are, in theory, and for small problems, we know how to do Bayesian posteriors. That's very generic. The other approach that people have explored is to make very strong assumptions about those distributions so that you can have analytic solutions or solutions that have easy numerical answers. But unfortunately, these assumptions usually are too strong. And so these methods don't work that great. We'd like to have methods where you don't make any strong assumptions except the kind of inductive biases that we know work well, for example, in deep learning architectures, but not so much about the distribution themselves too much. All right, and especially the form of the posterior. So like typically, people will assume that the posterior is unimodal, that it has only like one kind of solution and small variations around it. You don't want that. And the methods in standard variational inference will tend to find a single such solution and its small variance. But if there are many modes, many like different kinds of solutions, then these methods don't work well. So, and MCMC methods also have the same problem, that they tend to find one or two or very few solutions, very few modes, but they have a hard time jumping to a new mode that's far from the configurations they've seen that you visited. So why is it that using amortization, so training of something like a neural net, can help here compared to MCMC? Is because you can generalize from the configurations you've seen to potentially other good configurations. So whereas MCMC doesn't exploit any like learning, here we're going to be training this neural net that sees configurations that get different rewards, and that neural net can generalize. I mean, it's not guaranteed to generalize. Maybe there is no way to generalize. Maybe there is no structure. But if there is structure that allows to generalize from the configurations you've seen to others, which is really what generalization is about, then this kind of scheme could work. Also, one of the practical problems is the distributions we care about, as I said, have many modes. And how do we even represent distributions with many modes, right? Because if there's an exponential number of nodes, like think about a Gaussian mixture, you can have as many components as you want, really, in a Gaussian mixture. But if the number of components you need is exponential, then you're in trouble, both computationally and statistically. You have too many parameters. But there's another way, which is what is exploited in these GFlow nets, which is you decompose the generation of the objects you want to sample into a sequence of stochastic steps. So this is similar to what you find in denoising diffusion models, which are very popular these days for image generation. And by doing that, the number of modes you can represent can grow exponentially with the number of steps, which means you can represent very, very complicated distributions. Okay. Yeah, so we published this paper. I mean, it actually is going to be at the ICLR in a few days, that explains the relationships between GFlow nets and variational, or at least standard variational inference. So the main difference is that the variational inference normally uses the elbow, or like what's called it's a lower bound on the likelihood as the way to train the inference machine that samples the things you care about. Unfortunately, this tends to be mode seeking, meaning it tends to get stuck in finding one solution. It's kind of local minimum. And we explain how the approach that we're proposing is much more robust to this problem. And in fact, it can exploit ideas from reinforcement learning to explore the space in ways that in practice, in experiments, we can see can give huge advantages against the typical variational inference. We've also generalized this GFlow nets, which initially just for discrete random variables, to continuous ones. So this paper came out just a couple of months ago. And I want to spend the last couple of minutes to tell you about one of the papers that's related to causality, that where we use the GFlow nets to sample causal models, including the causal graph, but also the latent variables and the parameters. And the way it's done right now is that the GFlow net policy that we're learning sequentially adds one piece of the puzzle at a time. So in the case of the causal graph, maybe we start with an empty graph, and then at each step, we choose an edge that may connect these variables and form a directed acyclic graph. Once we have decided we have a graph, then, so there may be a special action that says, okay, we're done. We have the graph we want. Maybe it's the one G4 here. Then it might sample other things that we don't know, like parameters or the values of latent variables. And so this paper came out at last August at UAI, and it allows to represent a full Bayesian posterior over causal graphs. And since then, we've been working on several extensions of this. The last thing I want to mention connects back to my discussion regarding ChatGPT and these typical deep learning models that are very successful, and the problem of their not generalizing so well. So in the approach I've started to talk about with these GFlow nets, really, or in variational approaches, we are separating the machinery that does inference, like sampling answers to questions, like in these generative models, from the machinery that represents the knowledge about the world. So remember, I started about like, how do we use our machine learning methodology to represent how the world works, like the causal structure, for example. And in what I talked about somehow representing mostly the model, like with the causal approach with the Bayesian posterior, but we can also use this Bayesian posterior machinery to answer questions, to given some parts of the information, guess some other variables. But what I'd like to argue now is that typically the number of computations or the number of degrees of freedom that you need for representing how the world works is much, much smaller than the amount of computation and degrees of freedom that you need to specify how to answer a question. So like ChatGPT is just answering questions. It doesn't have an explicit model that you could somehow sample from or represent. And that's a problem. Like the two parts, the inference and the knowledge representation, like the model of the world, are confounded. And the model is actually implicit. It's not something that we have direct access in these large language models. And as a result, because there is this mismatch between the optimal capacity of the model and the optimal capacity of the inference machine, we end up with some choice which tries to do both. And so it's going to tend to overfit the world model. It has too many degrees of freedom, so it can represent more details than necessary about how the world works. On the other hand, it's going to be too small to do a good job of inference, and so it's going to underfit that inference capability. Furthermore, because we only have this one model that doesn't separate like how the world works from how to answer questions about it, it's very difficult to incorporate the kind of inductive biases I talked about at the beginning regarding causality. Now, what is important to realize is that when we train, for example, these GFlow nets, the inference machine that samples, say, answers to questions and things, we don't need to train it directly on the data. We can train it just to be consistent with the world model. So this is maybe an analogy to understand this is, think about AlphaGo, like the system, the deep net that was trained to learn to play Go. The world model here is actually not learned, is handcrafted. It's the rules of the game and how many points you get and so on. But what we train is the huge neural net that's trained to do inference, like how do I act in order to maximize the number of points or something. But when we train this, we have, you can think of two ways that it can be trained, right? It can be trained directly to imitate humans. So that's the way we train large language models right now. Or it could be trained with self-play, which is actually much more powerful, where it's just trying to behave in a way that's consistent with the world model, the rules of the game. We are in this situation where the description of the world model it could be very small, but the required inference machine needs to be huge. And when you train that inference machine, you can train it just to be consistent with the world model. You don't need to train it directly on the data, which means you're not limited by the amount of data when you train the inference machine. You're only limited by how many queries or examples you want to hallucinate from the world model. And thus you can afford, if you have enough compute power, you can afford a much larger inference machine. Okay, I think I'll stop here. I want to mention that we have written a tutorial on GFlow nets if you want to dig deeper, and we have like on the order of 15 papers already on this subject. So it started in NeurIPS 21, but since then my group has been very productive in this direction. So I'll stop here.
Many thanks, Joshua. Many thanks for your nice talk. And I think there are a lot of questions. I will first of all add all the other guys from the board of directors. So I would like to ask if Chiara, Marco, or Giuseppe would like to start with a question to Joshua.
Well, I can start with a question which goes more on let's say the practical applications of what you did rather than let's say the formalism. What I find very interesting here is let's say both this idea of, well, from the conceptual point of view, is let's say rethinking the separation between let's say the generation of the output and the representational part, which I think was kind of lost in the last 6 months, 1 year, 2 years or so, and is something we need to consider carefully. I mean, the interplay between these parts, but also really this idea of incorporating causality and having these kind of models especially for certain domains of application. I'm thinking of healthcare, or I'm thinking of
Yes.
very delicate domains.
In
where,
science,
for
for
instance,
example.
yeah, or science, where in a way Bayesian models are also already kind of important. So being able to, let's say, join these things and incorporate these techniques in these language in these large models, I think is very important and can prove crucial to have kind of certified or robust type of application that can be trustable, right?
Yeah, absolutely. In fact, I think, one of the things my group is doing, and that I find very exciting, is the application of these ideas in scientific discovery. So in a way, what I've been talking about is very much modeled by the way scientists discover things, right? So through a cycle of making sense of the data, but in a kind of Bayesian way, because we are conscious that could be multiple theories that explain the data, and different people may prefer one or another. But we kind of work with this notion that where we're not sure that our theory is correct, and in fact, this is what drives our experiments. So let's say we have two theories, we're going to design the next experiment to try to disambiguate the theories. So the whole process of experimental discovery is driven by a Bayesian posterior, or at least some approximation of it, that comes from human minds, in order to also be conservative. Like we as a good scientist should not be making strong statements that they're not absolutely sure of, or if they make statements, they can qualify them. And that's exactly what the right Bayesian behavior would be.
Okay, thank you. So we have questions from the audience. Sagar asks, any insight to how the world model is represented? How do you measure inconsistencies? Is done in a formal language?
Well, there are many ways you could do that, and I think the brain uses multiple ways to represent how the world works. So in what I talked about today, the world model is not represented as like one model. So it's not like we have a neural net somewhere that represents, oh, this is the causal structure, this is how variables are related. Instead, we have an inference neural net, which can, on the fly, generate the causal structure, the parameters, and everything. Now, which means that, today I can have a theory, and tomorrow I can have another theory. And humans, well, because of ego, like to stick to one theory, but I think good scientists can change their mind, realize that there are other explanations. So the world model is implicit, because instead of having one world model, we have this generative machinery which pops out pieces of theory. Actually, we don't actually get a full theory at any moment. Like, we have pieces of theory that are relevant to what we're seeing. And actually, that's one of the things we're working on in my group right now. How do we extend the work that I presented so that instead of generating the full theory, because humans don't do that, like we just generate little pieces at a time that are relevant. So that's yeah.
So Giuseppe.
Yeah, about this related to this. So when you do logical reasoning in general, normally it's very complex, no? So being exponential,
because the inference is intractable. The exact inference is intractable, right?
Exactly. So one of the most important things to do is actually to constrain, to limit the model. So
That's
actually,
right.
So not having a single model of the entire world, because this is going to be simply impossible to reason about, but isolate those elements on which then you do full logical reasoning, for example. I think I don't think the logic, I come from logic, I don't think the logic is the right answer with respect to isolate the right amount or the right elements in order to start doing reasoning, right? So this is more related to abstraction, and logic and abstraction, they never really work very well. Okay, so I wonder if in the next year, we're going to see a breakthrough of isolating small part of knowledge that then can be given to a SAT solver or to a linear temporal logic solver in order to do profound reasoning on these elements.
Right. Oh, so maybe I'm going to actually start by answering a part of the previous question, which is the way, once we sample like a model, like a theory, we can use it to check whether the data is coherent with that theory. So this is the reward function I was talking about, where you have the prior times the likelihood, essentially. So once you choose a theory, like a causal structure and parameters and so on, then you can measure how the theory is consistent with itself and how it's consistent with the data. That's the prior and that's the likelihood. So that's how you can validate a particular theory. And parts of the theory may be symbolic, like the causal graph is like a discrete structure, and parts of it could be continuous because maybe I need some parameters somewhere to represent continuous stuff. But it's important to know that the whole thing is probabilistic, because really it's not like we have a definitive answer to what the theory should be or what the explanations should be. You need probabilistic machinery to handle the uncertainty due to the ambiguity in the data itself. Like in a single example, there may be ambiguity. So we can't directly even apply a solver here because there's a lot of possible interpretations. And similarly, the theories themselves, like how the world works and so on, there's uncertainty because we see finite amount of data. And so the rational thing to do here is to be able to handle that uncertainty properly. And the Bayesian theorem basically tells us how to do that. What's interesting also about these methods where you generate theories on the fly is that it could be non-parametric. So I'm using a statistical term here, but what it means is that the theories can be like variable size objects. You can have a small theory that doesn't have like a small program. You can have a large program. And because you generate them on the fly sequentially by adding pieces to it, you're not like in the standard parametric setting where you have a fixed number of bits or real values that you're trying to figure out. And that is very powerful. And that's the way humans work. Like we observe some things and then we come up with theories or explanations that are simple. And then as we observe more things, we may come up with more complicated ones. That's Occam's razor. That comes out automatically of this probabilistic perspective.
Okay. So there is a question by Carlo. How rewards are assigned? Are we still in a reinforcement learning from human feedback fashion or something else?
Yeah, something else. So the rewards that I'm talking about are internal rewards. They don't come from humans or something like this. The reward here is, if you think of it like it's like the reward of truth, the reward of consistency. That's what reasoning is all about. You want to come up with a theory or an explanation for the data you see that is as consistent as possible with itself and with the things you observe. So that's the reward. The reward is how consistent is your theory and your explanation. You can compute it because given the theory and given the data, you can calculate. It shows like a bunch of probabilistic calculations, right? And if it's completely symbolic, it might be, ones or zeros. Like, everything is consistent. You got a 1 and you have one thing that's wrong and you got a 0, right? So probabilistic will be more robust, but that's the idea, right? It's consistency. It's an internal thing that's happening like in the mind of the machine. It's not about an action that the machine does in the world, and then you get a reward, which is the standard way of thinking in reinforcement learning. So these rewards are not, you acted well. These rewards are you building a consistent model of what you observed?
Okay, I would like to move a bit the kind of questions, and we'll go to something very recent. So you have been among those who signed an open letter related to to the fact that these kind of very big models of AI are becoming maybe too powerful in a too short time. So I would like to, we know that you are very, very concerned with the social impact of artificial intelligence. I would like that you comment on this open letter and maybe on your thoughts about that.
Yes. I'll just start by saying that I actually wrote a blog post that you can find easily on my website that goes into details of like my views about the letter, because I didn't write the letter. I signed it, which means I think it's a step in the right direction. Like, I'm not a big fan of the 6 months moratorium, but okay, so it sends a message. That's what matters. And the message is there's urgency to have regulation. It's a very simple message. And maybe it takes time. So self-regulation might be a good starting point, but eventually it has to come from governments. And even more than that, it has to be an international agreement. It's going to start by individual countries or EU and so on, putting out their own regulation, and many countries already started that process. Actually, in Canada, we're quite advanced. If everything goes well, we might have a law before the EU votes its own law. So why do I think it's important now? Well, because of ChatGPT. If you had asked me a year ago, yeah, I was pushing for regulation, but now I feel like it's urgent. And why is it that these large language models that, as they are behaving now, makes a difference? Because they pass the Turing tests. You interface with them and you're not sure if you're speaking to a human or a machine. And as Harari was writing in an article in New York Times a month ago, once machines can hack into our culture, they can pass for humans and interact with us with natural language. We are in a very dangerous and unknown and uncertain territory. So, I mean, can I be more concrete? Yeah. For example, there's already been a use of social media and email, like spam and so on, to try to influence people in their political opinions, right? Or for like cybersecurity attacks and all kinds of things. But now, but it was done by humans, and it was easy to detect that it was the same thing repeating if it was machines, and if it was humans, it's limited by the number of people behind the keyboard that can do these things. But now, if it's AI and you can't, it talks to you in a way that you don't know if it's a human. In fact, it can probably impersonate somebody that if there is enough information about that person online. So this becomes really dangerous, and we don't have the regulations to deal with that. And so, like in 6 months from now or a year from now, some big election may come up, and these tools could be used in ways that could be very destabilizing.
Okay, so we have other questions. So let's take these two further questions. Have you looked for biological interpretation of the different components?
Absolutely. I mean, my own research has been driven by the idea that there are general principles of intelligence that human brains exploit, and if we understand them, it's going to be much easier to build intelligent machines. But once we understand the principles, we don't have to copy machines, right? I mean, the brains. It's just like the analogy between planes and birds. And more recently, I mentioned the global workspace theory in my talk, right? So I've been focusing on what we know from neuroscience about conscious processing. So there's a sequence of events going on in your brain when you become conscious of something, and we know a lot about that. And actually, I wrote a paper recently about how subjective experience, which comes when you become conscious of something, may arise using machine learning concepts. So I think that this has been inspiring me a lot, but it can go also in the other direction, that what we're doing in machine learning inspired by neuroscience can inspire neuroscience and even philosophy in the case of consciousness.
Okay, thank you. Guido is asking a question about the gap between human and deep models. Some studies have shown that large language models can also predict brain recordings. Do you this alignment could be useful to validate models? Do you think this alignment?
Well, yes and no, because even if there may be shared principles, a lot of the details may be different. And I mean, the fact that first of all, it's not all the neural net models that fit well the neuroscience data. So for example, in the visual cortex, the first few years of development of computer vision models based on neural nets, they fit very well the cortical data. And as the models got better and better, they better and better fit the human brain data, or actually monkey data. But then more recently, like in the last few years, the models have continue to be better and better, but they fit less and less the brain data. So it doesn't have to be the same. But I think it's very interesting. For example, for neuroscience, what kind of neural net architectures better fit the neuroscience? Right. This can give a lot of clues in terms of a theory of how the brain works.
Okay. Just the last one from the audience, and what do enforceable regulation look like in this case? Sagar, again.
Well, I'm not an expert in law and so on, but we already have a lot of regulations for pretty much every aspect of society and industry that can touch a lot of people and can be dangerous to society. If you make food, or if you build chemicals, or if you build airplanes or cars, there's tons of regulation, and you have to document everything you do, and you can be audited. But in computing, there's nothing. I mean, there's the privacy laws, that thanks to GDPR and so on, but we're basically naked. So I think we don't need to necessarily be completely invent the wheel here. We already know about how to do regulation, and enforcement is never perfect. So you also need police that tries to go after the criminals, but it's better than nothing. Right now, it's really Wild West and law of the jungle, which is bad because there's a race to the bottom here to build systems that are not ethical.
Okay, on the same topic, I would like to conclude by asking you a comment on our European approach to artificial intelligence. So what about the AI Act, in your opinion?
Right. Well, first, it's great. I mean, first, it's great that Europe has been leading this. It's been the first country to be really serious about how to regulate. Now, I think it's 3 or 4 years now that this whole thing started, and it's not passed yet. So hopefully it will pass this year. And any law is better than no law here. Now, there are issues, I think, with, if I can comment on the European law, it's a big clunky piece of legislation with lots of definitions that are difficult to make. And it's not clear to me that it's going to be sufficiently robust to the evolution of technology. And when you have a clunky law like this, it might actually hurt more than it helps. Eventually, it might put a lot of unnecessary burden on companies, for example, and slow down innovation. I mean, regulation will slow down innovation, but we want to find the right compromise. So in other words, that we don't put unnecessary constraints on companies. But for that, you need a law that's, a legislative system that's more flexible. So the way that Canada is pushing forward right now has very high-level kind of law, which is what we call principles-based. So it kind of states ethical goals. And then the regulation is something that the civil servants will be able to adapt, which I think is crucial here because technology is moving so fast.
Okay. So thank you very much, Joshua. We have
My pleasure.
This concludes our seminars. I think that this was a great seminar for our community. So thank you again very much. And I think we can just send our appreciation, so virtually, but we really appreciated a lot your technical presentation and also your thoughts about an AI that is really trustworthy. So thank you very much, and I give to everybody the appointment to the next month. There will be Michela Milano with us. So bye, and thank you again, Joshua.
Ciao.
Ciao.
Right.